In this video, you will be introduced to the idea of logic. By the end of this video, you will be able to identify statements in logic, represent statements symbolically using 5 connectives, and distinguish between universal and existential quantifiers. At the core of logic is what we call a logical statement. This is basically a sentence that makes a clear assertion and can be judged as either true or false. For example, "The sky is blue" is a logical statement because it can be verified as true or false. Understanding these logical statements is key to identifying strong arguments, whether it's in math or in life decisions. In this video, we'll go over how to identify these logical statements, distinguish them from sentences that are not logical statements, and delve into why they are so crucial for logical reasoning. A logical statement is a unique kind of sentence, one that can be definitively labeled as either true or false, but not both. For instance, "It is raining outside" is a logical statement because it can be verified. In contrast, questions like "Is it raining?" or commands like "Close the umbrella" don't qualify as logical statements because they don't have a truth value. They can't be said to be strictly true or false. Understanding this distinction helps us to better grasp the building blocks of logical reasoning. Now let's break down how to identify a logical statement into 3 simple steps. First, ask yourself if the sentence makes a clear assertion that can be determined as either true or false. For example, "The Earth revolves around the sun" is a clear assertion that is true. Second, make sure the statement has a definitive truth value. That means it can't be both true and false at the same time. So, ambiguous or contradictory statements are out. Third, double-check that the sentence isn't a question, a command, or an expression of personal opinion or preference. Sentences like "What time is it?" or "I like chocolate" don't qualify as logical statements because they can't be definitively labeled as true or false. By following these steps, you can more easily identify what qualifies as a logical statement, which is essential for sound reasoning and decision-making. Now let's apply our 3-step criteria for identifying a logical statement using the sentence "The sky is blue." Step 1. Does the sentence make a clear assertion? Yes, it asserts that the sky is blue. Step 2. Can this assertion be determined as either true or false? Absolutely. On a clear day, the sky is indeed blue, making the statement true. So, by these criteria, "The sky is blue" is a logical statement because it fulfills both conditions. It makes a clear assertion, and that assertion can be verified as either true or false. Understanding this helps set the foundation for logical reasoning. Let's continue with our example sentence, "The sky is blue," and apply the final step in our criteria for identifying logical statements. Step 3. We ask, is this a question, command, or expression of opinion? The answer is no. It's a straightforward factual assertion. So, to conclude, "The sky is blue" is indeed a logical statement. It meets all our criteria. It makes a clear assertion. That assertion can be verified as either true or false, and it's not a question, command, or opinion. This sentence serves as an excellent example of what a logical statement looks like and underscores the importance of being able to identify such statements in logical reasoning. This skill is not just academic. It has practical applications in both mathematical reasoning and our everyday decision-making. Recognizing logical statements helps us in several ways. For one, it enables us to engage in constructive debates. Secondly, it allows us to craft valid arguments that stand up to scrutiny. And most importantly, it sharpens our critical thinking skills. Being able to differentiate between statements and non-statements adds clarity to our discussions and helps us avoid confusion and ambiguity. Remember, by following the steps we've outlined and practicing with the examples given, you'll become proficient at identifying logical statements in all sorts of situations. This skill set is more than just academic. It's a tool for clearer thinking and more effective communication. These connectives allow us to combine, relate, or even contrast simpler statements to form more intricate ones. We'll be focusing on 5 primary logical connectives. Conjunction, represented by and, combines 2 statements so that both must be true for the compound statement to be true. Disjunction, denoted by or, makes a compound statement true if at least one of the simpler statements is true. Implication, often stated as if, then, sets up a relationship where if the first statement is true, the second must also be true. Biconditional, which is IFF or if and only if, states that 2 assertions are true or false together. Negation, represented by not, reverses the truth value of a statement. Understanding these connectives is crucial for symbolically representing logical statements, which we'll explore in detail in this handout. So, in essence, these connectives serve as the building blocks for constructing and analyzing more complex logical arguments. These symbols are shorthand ways to write logical statements more efficiently and are commonly used in mathematical logic and computer science. Conjunction is represented by the symbol that looks like an upside-down V. Disjunction is represented by the symbol that looks like a V. Implication is denoted by the symbol that looks like an arrow pointing to the right. Biconditional is represented by a symbol that looks like a double-headed arrow. Negation is denoted by a symbol that resembles a sideways L. By familiarizing ourselves with these symbols, we can more efficiently read, write, and analyze complex logical statements, whether in academic settings or when applying logical reasoning to real-world scenarios. The key to logic with symbols is the primary connective word. This is a 3-step process to translate complex logical statements into their symbolic forms, making them easier to analyze and manipulate. Step 1. Start by breaking the compound statement down into its simpler parts or constituent statements. These simpler statements are often represented by letters like P, Q, or R. Step 2. Next, identify the logical connective being used in the compound statement. Is it an and, an or perhaps an if, then? Step 3. Finally, take these simple statements and combine them using the appropriate symbolic connective. For instance, if your simple statements are P and Q, and the connective is and, you'd write this symbolically as P and Q. By following these steps, you can efficiently convert complex logical statements into a symbolic form, facilitating easier analysis and understanding. Here is an example. If it is raining outside, then I will take an umbrella. Step 1. First, we break down the statement into its simpler parts. Let's represent. It is raining outside with the letter P and I will take an umbrella with the letter Q. Step 2. Next, we identify the type of logical connective being used. In this case, it's an implication, often expressed as if, then. By doing this, we're prepped to symbolically represent this complex statement, which would be P then Q in symbolic form. This methodical approach allows us to dissect and understand logical statements, making them easier to analyze and work with. Step 3. We combine the simple statements P and Q using the appropriate symbolic connective for implication, which is the side arrow. Thus, the symbolic representation becomes P implies Q. In conclusion, the statement, if it is raining outside, then I will take an umbrella can be neatly and efficiently symbolized as P implies Q. This allows for easier manipulation and analysis of the statement in logical or mathematical contexts. Mastering these elements is not just academic, it's foundational for logic and critical thinking. Why does this matter? Well, being proficient in these areas helps you in several ways. First, it allows you to construct valid and compelling arguments. Second, it's essential for computer programming, where logical operations are fundamental. And third, it simplifies the process of analyzing complex logical assertions, breaking them down into more manageable parts. By practicing with the examples and following the steps we provided, you can refine your skills in symbolic representation. This will not only make you more logically adept, but also equip you to tackle complex logical puzzles with ease. Quantifiers allow us to make generalized statements about elements within a set, or about the set as a whole. There are two primary types of quantifiers. The universal quantifier, which essentially says something is true for all elements in a given set. The existential quantifier, which states that there exists at least one element in the set for which a property is true. Understanding the nuances between these two types of quantifiers is crucial for deeper insights into logic and mathematics. This video aims to clarify these differences by providing clear examples and practice problems, allowing you to become proficient in using these essential logical tools. First, we have the universal quantifier, which is often represented by an upside-down A. This quantifier essentially means for all or every. If a statement uses this quantifier and that statement is true, it's a way to say that the condition or property being described applies to every element in the set under consideration. Secondly, there's the existential quantifier, typically symbolized by a backward E. This one means there exists or for some. When a statement employs this quantifier and turns out to be true, it tells us that at least one element in the set satisfies the condition or property being discussed. Understanding what these types of quantifiers signify is crucial for anyone who wants to delve deeper into the realm of logical and mathematical reasoning. Step 1. First off, determine what kind of quantifier is being used in the statement. Is it saying something about every member of a set, which would be the universal quantifier, often represented by an upside-down A? Or is it saying that there exists at least one member in the set that fulfills a condition, indicated by the existential quantifier, typically symbolized by a backward E? Step 2. Next, identify the domain or the set of items or individuals over which the quantifier is applied. Knowing this domain helps you grasp the scope of the statement. Step 3. Finally, understand the real-world or mathematical implications of the quantifier in the statement's context. This will tell you if the statement applies to every element in the set or just at least one. By following these steps, you'll be better equipped to understand, analyze, and even create your own statements involving quantifiers. Let's look at an example. Step 1. The statement is talking about every student, which indicates the use of the universal quantifier. This is often symbolized by an upside-down A. Step 2. In this case, the domain or set over which the quantifier is applied comprises all students. That means the statement is making a claim about each and every student within that particular set or group. By going through these steps, we can see that the statement is a universal claim, saying that each student in the set of all students has passed the exam. This is a useful way to dissect and understand the underlying logic of the statement. Step 3. The real-world meaning of this statement is straightforward. There is no student who failed the exam. In other words, all students meet the criteria of having passed. Conclusion. The statement can be symbolically captured as follows. For every individual X, if X is a student, then X has passed the exam. In symbolic logic, this is usually represented using specific symbols for all and implies. Here, X is a variable that can represent any individual student in the set of all students. By following this method, we've taken a sentence in everyday language and translated it into a precise, logical form. This helps in deeper analysis and a clearer understanding of the statement's meaning. These tools are more than just symbols. They are foundational for anyone wanting to delve deep into mathematical logic. Why is this so crucial? Well, these quantifiers enable us to make precise, clear statements about sets or collections of items or individuals. When you understand the difference between saying something applies for all members of a set versus saying it applies for at least one, you arm yourself with the ability to navigate and understand complex logical statements. By mastering these quantifiers, you're well on your way to engaging with mathematical logic with a level of clarity and confidence that will serve you well in many contexts.